Hello, my name is Anastasia. I would like to share with you my animation slideshow. Without further ado, I will start with linear regression. Body mass index to estimate individualized patient radiation dose in abdominal CT used for this example. First of all, a graph with x and y axes are made. The y for effective dose in millisievert, x for BMI. All data in a certain population as dots put inside this graph. A diagonal line is drawn to determine the overall relationship between all the dots. To determine each patient effective dose, a vertical line from the x-axis that intersects this diagonal line is made to make another horizontal line that gives results to this effective dose in y-axis. For example, patient A with BMI 20 kg per meter square. A vertical line that intersects the diagonal line from the x-axis is drawn, intersect this diagonal line, and make another horizontal line, giving a result to 3.00 millisievert effective dose. The same goes to patient B and patient C. The next, naive Bayes. For example, there are 100 images of knee X-rays which has been labeled with osteophyte and joint space narrowing features. From all 100 images, we split them into two categories, osteoarthritis as many as 25 images and the other 75 images. The computer was then asked to detect osteophyte features among both groups, and it found 15 images with osteophyte in the OA group and 3 images in the non-OA group, which makes the probability of osteophyte detection belongs to the OA group as much as 60%. Joint space narrowing feature is detected as many as 20 images among the OA group and 5 in the non-OA group. Thus, the probability of a joint space narrowing feature belongs in an OA group is 80%. When both features are combined, the computer found 25 out of 25 images in OA group has osteophyte and joint space narrowing features, while only 1 in the non-OA group, which makes the probability of osteophyte and joint space narrowing features belong to OA group 100%. Other features can be added to give a better and more accurate result, such as subchondral sclerosis, deformity, and others, which give results to certain probability, and when all features are combined, the result will have higher credibility. Postscript, the labeled feature must be trained first so that the algorithm can detect each features. Decision tree. For example, a table as an input data of the body's component Hounsfield unit density has been provided. Then the computer will try to split the data to make a good tree. The data provided is best split using density first as the root, with next different density and isodensity. Isodensity doesn't have any other branch. It will directly result to muscles or brain. However, different density can be split into two, which are increased or decreased density, hyper or hypodense. Hyperdense will make another tweak, which is the Hounsfield unit value to split the data. If the value less than 1,000, the final point is calcification, while more than equal 1,000, the final point is bound. For hypodense, tweaks are made using the Hounsfield unit as well. When more than equal minus 900 value, the final point is fat, and the other will be air. Random forest. For instances, lung consolidation on CT scan can have diverse interpretations such as edema, hemorrhage, pneumonia, contusion, or bronchoalveolar carcinoma. From this data presented on Table 2, we will try to make several trees. The first tree can be made using acute onset as root, and the first branch, the alveoli content. Is the alveoli content pus? If the answer is yes, then goes to pneumonia. If the answer is no, then goes to bronchoalveolar carcinoma. The root for the second tree can be structured using diffuse consolidation pattern. If the answer is yes, it goes to alveoli blood content as the twig. If the answer is yes, then goes to hemorrhage. If the answer is no, then goes to edema. If the pattern is not diffuse, the alveoli content is blood, then it is a contusion. However, if the alveoli content is not blood, it becomes false since it's not provided in the data. The third route is the water content. If the answer is yes, then it is edema, while if the alveoli content is not water, it should be divided into chronic onset or not, and if it is yes, then goes to bronchoalveolar carcinoma. If it is no, then false. For an example, patient A with chronic onset and the images shows lobar consolidation pattern with cellular content on the alveoli. From the first three, is the onset acute? No. Goes to bronchoalveolar carcinoma. From the second tree, is the pattern diffuse? Yes. The alveoli blood content is not blood, then edema. From the third tree, is the alveoli content water? No. And the onset chronic? Yes. Then the majority vote from all trees is bronchoalveolar carcinoma. Support factor machine. For SVM illustration, we will try to differentiate between a cyst and a solid nodule. Lower density and sharp margin is the feature of a cyst. However, higher density with more irregular margin is the feature of a solid nodule. But how can a computer distinguish if there is a nodule which is more like a cyst or vice versa? A graphic linear is made where the x-axis is the density features from low to high, and the y-axis represents the margin from irregular to sharp. All prior data collected is put inside this graph. Afterwards, the image will be segmented and classified using this graph by finding the best hyperplane and the margin, which is found by drawing a parallel line from the nearest data to the hyperplane in each class. The bigger the margin is, the better the computer works. And to achieve a larger margin, lots of data with all kinds of cysts and nodules should be added. This method is called linear SVM, which only works for linear data, while nonlinear data cannot use this linear method. Hence, another trick, such as kernel, can be used. A line couldn't be drawn if the data is not linear. Hence, a curve should solve the problem. The kernel method uses a separation plane by drawing a three-dimensional graph with x, y, and z axis. From the input data, we could draw the first two-dimensional graph with the very bottom cyst is on x3, y0. Solid nodule above it is on x2, y1. Another solid nodule on top is on x1, y2, while the top cyst is on x0, y3. Then we need to separate the light blue and the dark blue dot. There are three formula options to help classify the two. The first is x plus y, the second is x times y, and the third one is x squared. The x times y equation seems to give a better result, which can help to distinguish the cyst and nodule. X times y for the light blue is 0, and for the dark blue is 2. And what can separate 0 and 2? The answer is 1, which is x times y equals 1. And the same with y equals 1 per x. And this rescue equation results in exactly hyperbole curve. And this is a kernel trick. So we have our z-axis, which is x times y. And we put together the x, y, and z axis, which is the x times y, and we calculate all of them, the coordinate. For the first on top, the cyst is 0, 3, 0, and the second is the nodule, solid nodule, is 1, 2, and 2, and another nodule, which is 2, 1, and 2, and the bottom cyst is 3, 0, 0. A three-dimensional graph is made with all data with its x, y, and z value is applied on this 3D graph. The first one is the cyst, belongs to 0, 3, 0, and we can put it there, 0, x, 3 for the y, and 0 for the z. The next is the nodule with 1, 2, 2, and it will be here. And the next nodule is 2, 1, 2, and the last cis is 300. Then we get the separation plane. Next is hierarchical k-means clustering. I'm using an example to cluster TNM stage 4 nasopharyngeal cancer based on AJCC 8th edition. The data is given in X, Y, and Z axis, which are T, N, and M. And those data will be clustered in 5 different staging. There are 5 centroids randomly placed among the data to make the cluster. Each dot nearby each centroid will be clustered and turn the dot's color into the centroid color. Then the centroid will move to the center for each cluster. Reclustering occurs until the best fit selection is made. Finally, after several cluster and reclustering, we can see that 5 clusters have been made. T1 N0 without metastasis is clustered as stage 1. T1 or T2 N0 or N1 M0 is stage 2. T1 or T2 or T3 N0 N1 or N2 without metastasis is stage 3. T4, N0, N1, N2, or N3 without metastasis is stage 4A, while T1 or T2 or T3 or T4, N0, N1, N2, or N3 with metastasis is stage 4B. A quick reminder, on the real world, there is no guarantee that in the end of the iteration the groups will correspond exactly to each stage. This is solely just in illustration, hence the need of radiology is indeed needed.
Logistic regression. An example to determine ACL injury or normal ACL on knee MR is used to portray this method. The two features are anterior translation with cutoff measurement more than 7 mm and Blumenstadt angle more than 15 degrees are used. All data is put into this graph as dots. The green dots represent data with normal ACL, where the blue are with ACL injury. Then we draw a line to separate the two classes. For example, patient A with anterior translation 8 mm and Blumenstadt angle 20 degrees. If we put each value in the X and Y axis, it falls into the ACL injury classes, which is correct. This measurement is in tune with the cutoff for ACL injury. Patient B with anterior translation 3 mm and Blumenstadt angle 5 degrees. The intersection falls on the normal side, which is also correct. Patient C with anterior translation 6 mm and Blumenstadt angle 15 degrees. The intersection falls on the ACL injury side. However, this does not meet the cutoff measurements for ACL injury. Hence, we should train and change the data that if the data is nearby the line, it should be turned into normal ACL due to its coincide value. Therefore, no longer a simple line can split the two classes. Perhaps a curve or round shape or even two lines, which is called a neural net, will help.